Quantum Teleportation Protocol helps in sending the qubit state from one location to another, even if they are far apart. It has many applications, in particular in quantum communications. However, it requires entanglement in between. This is Taha Selim, and today we will dive into Quantum Teleportation Protocol. Let's have a quick overview of quantum entanglement. Quantum entanglement requires two qubits to work. It means that perform operations, two particles or the two qubits, and correlate their states, in a sense that if we measure one, we know the second for free. So there is many aspects in quantum entanglement, but now let's first draw the quantum circuit and see. So let's imagine a 2-qubit quantum computer. Let's have the two qubits. We will call the first one Q0 and the second one Q1. They are initialized the ground state, which we denoted, as we have seen in the previous video, as kit 0. Now we make these lovely wires, and entanglement can happen because of the action of two unitary operations. First, applying the Hadamard gate on the first qubit. Second, applying what we call controlled X or Pauli X gate or controlled C0 gate. So this one called gate or Pauli CX. So let's see the action in detail. What does Hadamard do? If Hadamard acts on a kit 0 or a qubit in the ground state, it projects it in the superposition situation. So it makes it half in the ground state and half in kit 1. We call it the excited state, for example. So that's what will happen. The action of the Hadamard gate will bring this qubit into a superposition. The action of C0 gate, it's actually can be seen from the following truth table. C0 gate has something like this, like a node, the gate itself, which is X, and this is called control gates. It means that this node samples what happens to the control qubit. So this is, and it actually samples what happened to this particular qubit, and based on if this qubit is 0, don't do anything, don't apply the gate. If the qubit is 1, apply the gate. So in that sense, we apply X gate if only if the first qubit or this particular qubit Q0 is in state 1. So now we have two actions. We have first the action of the Hadamard gate, and this leads to superposition of the first qubit, and then we'll come to the action of the C0 gate or the CX gate, and this is, we will leave the normalization factor as a Z, and then now we would like to add the second qubit. So if the first qubit is 0, we don't do anything to the second qubit, we leave it as a Z, 0, as it was initialized. And if the first qubit is 1 or in state 1, we flip the state of the second qubit, this qubit Q1. So it was 0, then it goes, instead of 0, it goes to 1. So this is what we envision by a quantum entanglement. I'm going to draw the circuit a bit nicely with our initialization of the qubit Q0 and the Q1. We have here the Hadamard gate followed by the action of CX or C0 gate. The Hadamard gate put this in a superposition, and the CX gate, depending on the value or the state of the Q0, specifies whether or not can apply the gate X on the second qubit. So hence we end up with this particular state Q0, Q1 will be 1 over the square of 2 kit 0, 0 plus kit 1, 1. And here is the thing. We have now two correlated measurements. So if we know or we perform a measurement for the first qubit and we found it is in the 0 state. So if first measurement we find that Q0 is in the 0 state, we get for free that Q1 it is in the 0 state, because this is the only configuration at which both qubits are in zeros. So if I know the first one, definitely I know the second one for free. Similarly, if I perform another measurement, if I have the first qubit is in 1, then I get the second for free in 1 state. Similarly, if I perform a measurement and I find qubit 1 in 0, I would know immediately that for free that Q0 is 0. And if qubit 1 is in 1, qubit 0, it is in 1 state. So there are three elements to the entanglement. There is intuitive element, physical element, and also mathematical element. Intuitive element, if I measure the first one, I get the second for free. It's something okay. If I have two identical twins for 100%, if I know the personality of the first, I would assume I would know the second for free. So I don't need to meet the other twin. Physically, those measurements are correlated. So if I measure the state and I know the state of the first particle, the second is known already because they are correlated or they are entangled. mathematically that state cannot be defactorized. So I cannot separate those states to the initial qubit states that they are formed from, because here they are maximally entangled. So far we have initialized qubits in the ground state, which is in kit 0 all the time. And then we have performed our unitary operations, which includes acting with the Hadamard gate on the first qubit, and then the CNOT gate, which has control, and the target here. Based on the state of the control, we apply the target or not. However, those two qubits are initialized in the ground state. We can have other values, or we can initialize them differently. So we can initialize them, for example, in state 0, 1, can initialize them in state 1, 0, and also we can initialize them both in state 1. So how the entanglement would be if we initialize the qubits differently from pure 0, 0 state? Let's see. So I'm gonna now divide into 4 sections. We'll see why in a minute. Here we have our own typical initialization, the qubits, which is done in state 0, 0, and then we apply our Hadamard gate, and then we apply the CX gate. The action of the Hadamard gate will make the first qubit in state 1 over root square of 2, 0 plus kit 1. If we apply the CNOT gate, then depending on the state of the first qubit, we specify whether we apply the action of the X gate or not. And the X gate will invert the qubit, as we have seen in the last video and in the last few minutes. So now we have kit 0, in which the first qubit is in the 0 state. So the CX gate will do nothing. So it will leave the second qubit as a Z, which is now in state 0. And then if the first qubit in state 1, it will flip the state of the second qubit. And the state of the second qubit, it is in 0. So we flip it and make it 1. Okay, that's nice. We have now the default situation from 0, 0. Let's now initialize them differently. And we initialize them where the first qubit is initialized to 0 and the second is initialized to 1. And let's apply our Hadamard gate and our CX gate. The first action of the Hadamard gate will do the same. I know that Hadamard gate, when it acts on the kit 0, puts the state in a superposition of kit 0 plus kit 1. Now, when I apply the CX gate, it leaves the normalization factors is unaltered. Then I look to the first kit, this one, and the state of the first qubit is in 0. So I leave the second with untouched, and the second is initialized to 1, so I leave it 1 as Z. And then I come to the second. In the second, the first qubit is 1, so when it is 1, it flips the state of the second qubit. I get 0 here. So these are two entangled states, because now we have two configurations, two unique configurations now, in which if I know the state of the first qubit, I get the second. So if the first state of the qubit is 0, I know the second is 1. If the state of the first qubit is 1, I know the second is 0. So that's pretty clear and pretty obvious from the expression. So that's another entangled state. Let's now see a different initialization. Can have initialization where the first qubit is 1 and the second is 0. We apply also the same, our Hadamard gate and our CX gate. And then let's study the action of those gates on the qubit. Hadamard gate, when it applies on a qubit in state 1, acts differently, and differently it just changes the sign in the middle, so that sign is changing. So if I summarize that action of the Hadamard gate, I will find that when H acts on 0, projects it to this superposition state with plus in the middle, here is the plus, and when it acts on a qubit in state 1, it has minus in the middle. And this is, of course, could be driven easily, and this is, of course, could be derived easily from the matrix multiplication of the Hadamard gate times the vector representation of the qubit state. This is a minus. Now we're back to our nice representation of this different initialization. Then we write our initialization here and the action of the Hadamard gate on qubit 1. Then we get kit 0 minus kit 1. Then now we study the action of the CX. It does nothing to the normalization factor. And then if the first qubit has a state 0, it does nothing to the second. And if the state is 1, it flips the second. So the second is initialized to 0, it now will become 1. So we have the same situation or the same representation here, similar to this one, but with a different sign. So that's also another entangled state. If we know the first one of the states of the qubit, then we would know the second for free. And also it cannot be defactorized again, and the measurements are correlated. Can also initialize both of them in state 1 and apply our unitary operators. Then let's study the action. We know now that the action of the Hadamard gate will project this in the superposition of kit 0 minus kit 1, and then the CX gate will just act on that and will leave the normalization factor unaltered. And then we'll have kit 0 0, because if the first qubit is 0, it does nothing to the second one, minus, so that will be 1, sorry, it will do nothing, minus if the first qubit is 1, it flips the second, so it makes 0. So that's also another entangled state. So now we have a unique situation. We have 4 representation, or we have 4 states, which all of them are entangled. So those states are called Bell states. And Bell states are orthonormal bases, so they can form a space by themselves. And actually what the Hadamard gate with the action with the CX gate, they do a transformation, or they do a rotation from these computational bases, or this computational representation in terms of zeros and ones, from this to another representation which is called Bell space, or the Bell representation, where we can form a basis or representation out of these 4 states. So in a summary, if we have qubit Q0 and then qubit Q1, we act with Hadamard gate, and then we act with the CX gate. So we can form the table of the 2 qubits here, Q0 and the Q1. If the first qubit and the second are initialized in state 0 0, then we have 1 over its square of 2, 0 0 plus kit 1 1. If they are initialized in state 0 1, we have, as a result of applying the Hadamard plus the CX gate, 0 1 plus kit 1 0. If you are in state 1 0, 1 over root square of 2, kit 0 0 minus kit 1 1. Yeah, that was a nice bird. And then we can initialize them in ones. And then we have 1 over root square of 2, kit 0 1 minus kit 1 0, and these are called Bell states. That's computational bases, and these are Bell bases. And of course, Bell states or Bell bases, they are very important in quantum mechanics and in quantum computing, in particular for quantum teleportation protocol that we are going to discuss in a minute. And the quantum teleportation protocol is basically has 2 main actors or 2 main players. They are like Adam and Eve, and Alice wants to send to Bob a secret message that is encoded, for example, on a qubit state, or the qubit state by itself. So she has to apply the quantum teleportation protocol together with Bob, and this has certain conditions. First, minimally, Alice should have 2 qubits. This is the qubit that has a secret, and we can call it state psi, which is A times 0 plus B times 1. So this is my secret. Of course, this is not mine. This is Alice's secret, and she wants to send this secret that could be, for example, some encoding from a different information or so, but she would like to teleport or send this state from her location to Bob's location. So Bob's need to have 1 qubit in order to receive state or the secret state that Alice wants to send. For this protocol to work, the second qubit, so this is the first qubit, this is the second, this is the third. Protocol to work, these 2 qubits, Q1 and the Q2, they should be in entanglement or in entangled state. So here the entanglement is playing an important role because it's would deliver or would transmit the message from Alice to Bob. These should be in entanglement, these 2 states, and then Alice has to do some things to send the state, and of course Bob has to do also some post-processing for the state in order to retrieve the message correctly or the state correctly that Alice has sent him. So let's make the drawing of the quantum circuit. We have here 2 qubits, Alice. This is the one that has a secret, and these 2 qubits are entangled. So those ones already have been entangled using a previous circuit, and they are in one of these Bell states. So let's call it B00, which is 1 over root square of 2, kit 00 plus MolKet 1-1. This is the entanglement state of the second and the third qubit. And of course, this is the one, those are Alice, and this one only for Bob. So we can make a separation here. It belongs to Bob and what belongs to Alice. So to create the entanglement, we have seen the circuit now in the previous few minutes. We have to use the Hadamard gate followed by the action of the CX gate or the C0 gate. So this unitary operator will map or will convert these individual qubits, Q1 and the Q2, from, for example, being independent from one another to be entangled, and in, like, for example, in state 00 and state 11. So to reverse the entanglement, quantum mechanics allows us to apply the operators in a reverse way. So let's reverse the order of the Hadamard gate and the C0 gate. And first apply the C0 gate followed by the Hadamard gate. Let's do that. So in this time, we have here the secret state psi. We will not touch it now. Then I have here first Hadamard gate, and instead of applying this one, we'll apply directly the CX gate, followed by applying the Hadamard gate. Then Alice should perform measurements, and she will communicate those measurements results to Bob. So now Alice will perform the CX gate first, followed by the action of the Hadamard gate. And then she will get a particular state, and then she will perform the measurements of both qubits. So she can get for a state of the qubit 0, it could be in state 0 or 1. Similarly, for qubit 1, it could be in state 0 or in 1. And then Alice should communicate those keys or those findings with Bob. She can use Morse code, she can use anything of encryption, but she has to do it via a classical broadcast. She can even call him on phone, Bob 00, Bob 01, Bob 10, Bob 11. But of course, they have to know the convention, if it is big Indian or little Indian. This is a different story, but it matters where you start the counting of the qubit. Do you start them from left or right? Yeah, it might be a bad joke. So she will only need to send 2 digits to Bob, either informing him about the state, her findings, maybe the state 00, state 01, 10, and 11. Based on those measurements or those information, Bob has to do certain post-processing. And this post-processing would allow Bob to retrieve the state that has been sent to him from Alice, to retrieve the state psi. So at the end, Bob will get the state psi, this one that has been transmitted secretly from here to there, and Bob will get it only if he has done properly the post-processing. And to do this post-processing, he will need these inputs of the measurements from Alice to tell him via a classical broadcasting channel. This is the situation of Alice. It has 2 qubits, Q0 and Q1. Q0 has this mysterious state psi, and then we will apply Hadamard gate. So every time I apply it in the entanglement way, so we apply the CX gate, and then we apply the CX gate followed by the Hadamard, and then there is measurement to perform. And of course, this is the qubit of Bob, which is Q2, and qubits here are already entangled and they are in a Bell state. We call it B00. So now, what could be the findings of the measurement? We have seen it. Qubit 0 could be in state 0 or 1. Similarly, qubit 1 could be in state 0 or 1. So we will have an action table or a measurement table in which we write the state of qubit Q0, qubit Q1. So she can tell him that 2 qubits, when they were measured, they are in state 00, could be in state 01 or 10 or 11. Now, if she informs him that she found the 2 qubits in state 00, Bob has received already the state psi, so he has nothing to do basically. So the state that he received is the correct state processing. He heard her telling him that she measured the 2 qubits in state 01. It means that he has to apply post-processing by applying the phase flip Z on the received qubit. So now This is the received state. We call it psi prime. Correct state is psi. And it means that in the first situation, psi is just psi prime. But in the second, psi is a correction of psi prime by applying the z gate on the psi prime. Now, if she tells him she found the state, she found the measurements of the 2 qubits in state 1, 0, then this means that he has to apply the NOT operation, so x on the prime. And if she tells him in a state she found the 2 qubits in state 1, 1, then he has to apply both x and z on the psi prime. So these are the post-processing actions that Bob has to do when he hears the information, or based on the information that's provided to him from Alice's side. So this post-processing, it could be programmed on a computer, it could be done automatically, and so on. So this is something natural, and he can perform these post-processing actions based on the measurements input from Alice. We can write this general post-processing procedure in generally, and this is x to power q0 times z to power state of q1. And you can see it. If we are here, we only have the z gate. If you are here, we only have the x gate, and if you are here, we have 2 gates. So that's sort of the general procedure. And here is the thing, we have several questions about this, but the most important one, why we need to perform the measurements in the first place to send the qubit state psi from Alice's location or from Alice's qubit to Bob's qubit or Bob's location. And the answer lying in the non-cloning theory. We cannot create a copy of a quantum state without destroying the original copy. So Alice has a state, and that copy has to be destroyed first by performing the measurement. So the superposition would collapse and the quantum state will be disturbed by the measurement process, and then it will be destroyed. And at that moment, Bob is allowed to get the quantum state. And this is a fundamental limitation of the quantum mechanical nature. By this, I hope I made the quantum teleportation protocol easily communicated to you and illustrated it. For more mathematical insights, how this is done, please follow my tutorials, and also the lecture notes and documents on GitHub and other websites. So stay tuned for future tutorials. Don't forget to listen to the other podcasts and other presentations as well about the quantum technologies and high tech. Have a great weekend.